Good morning, everyone. So, welcome to this morning's session. Just a couple of announcements to get started. Would anyone who's got a talk today that they haven't handed in the PDF yet, could they do that as soon as possible to the desk, please? And the other thing is about posters. The organisers are keen to collect the PDFs of all the posters that are shown, so that these can be put online with other things. So anyone with a poster and a PDF file, could they also hand that into the desk, please? Okay, so this morning's session is about complementarity of Planck and other experiments, and we're very happy to have four very distinguished speakers to take us through to coffee. And the first one of these is G.Hinshaw from UBC, and he's going to tell us about final results from WMAP, or WMAP in the Planck era. So, Gary.
Thank you. Let's see, I guess I need to be two-fisted here. So, thank you to the organizers for inviting me to talk about WMAP one last time, and pleasure to be here. So this is the final results from WMAP, the 9-year data, and some discussion about WMAP in the Planck era, and some of my thoughts about some of what I've seen from the Planck data in comparison to WMAP. All of it very preliminary, but it's been fun to think about for the last couple of weeks. So just to remind you, this WMAP was launched in 2001 to an L2 orbit, began observing in August of 2001. Spent 8 years at L2 and was given a Viking funeral in September 2010, sent to essentially a solar orbit, 1.07 AU, where it now rests for quite some time, hopefully. I just want to highlight the differences between WMAP and Planck instrumentation, just to remind you of a few ways in which we are complementary. It's similar coherent detector HEMP technology to the LFI. 10 what we call differencing assemblies is spread across 5 frequency bands from 22 to 94 gigahertz. And the takeaway basically is that it's differential. It's 5 frequency bands, coherent detection, and it's differential, so it has 2 lines of sight on the sky and takes temperature differences rather than total power measurements. And the scanning strategy is a little bit different from Planck's. Because we're differential, we do a spin and precession combined to cover a large portion of the sky every hour, 30% per hour, roughly. And we get a lot of different angles of attack on any given pixel on the sky, especially, of course, near the poles, but also a fairly good variety even at mid-latitudes. And just like Planck, cover the sky every 6 months and do so repeatedly. Let's see. Okay. So just a few comments on the stability of the instrument over the years. We don't often show these plots, but these are just some calibration parameters from one of the channels, plotted as a function of time. So this is actually from the 7-year data, so this is a 7-year plot. And the top panel here is showing the one of the calibration factors, just the straight conversion from volts to millikelvin on the sky. And I just want to make the point here that it's varying due to primarily due to thermal effects, and also a secular term due to aging, and the scale of this variation is about 2% over the course of the mission. And so it's a very, of course, L2 is a wonderful environment for doing these kind of observations, and essentially the only real thing we had to deal with calibration-wise was fitting a thermal model to that, which was non-trivial, but it wasn't too challenging. And then the instrument baseline, we're differential, so we tell our 0 point, the 0 point of our system, by spin flipping. Every half cycle we flip the sign of the sky signal so that the time average of the sky signal is 0. That tells us what the instrument baseline is, B, and this is a plot of that as a function of time over the 7-year mission 2 for one of the channels. And that's varying by about 5 millikelvin over the course of 7 years. So pretty rock solid environment, and as a result, only less than 1% of the data, of the entire mission data, was flagged as unusable over the course of that time. And I'm sure you've all seen at least something that looks equivalent to these, if not the 9-year maps, then the 7-year maps, which are visually identical. 5 frequency bands going from K up in frequency 32, 33, 41, 61, and 94. And then the corresponding polarization maps presented here as the color here represents polarization intensity, square root of Q squared plus U squared, and the arrows indicate directions in pixels that have signal to noise of at least 1 on a 2-degree patch, which in the higher frequencies is not very many, actually. So, and everything in this, every visual signal that you can see in the polarization maps is galactic foregrounds. The detection of polarization in the CMB is purely statistical. And so this is really the core legacy product of a WMAP mission. And I think it's fair to say that the K-band data, especially the K-band polarization data, will continue to be of use even into the Planck era. I'm quite confident of that. And the temperature for foreground studies. So I wanted to say a little bit about foregrounds. In the 9-year analysis, we actually spent some time trying to understand this increasingly complicated diagram of what the foreground components around the CMB window are. Not with as much success as I would have hoped. This is the nice thing about foregrounds is it's really easy to get rid of them if you just want to do cosmology in the temperature regime. It's much harder to actually understand the foregrounds and to try and disentangle this mess of radio components that shows up on the low frequency side. So this is just a reminder, the total foregrounds have a window at about 60 gigahertz. The WMAP bands don't show up that well here, but K band is down here or W up here. And our lowest 3 frequency bands are kind of really trying to nail the synchrotron, thermal Bremsstrahlung, and the relatively newly realized spinning dust or anomalous emission term. And let's see, I'm not sure if the colors actually come out. This is supposed to be a 3-color image of no modeling here, but these are just band differences of the 5 frequencies designed to highlight the different components here. So the, oh, sorry, wrong button. In orange, that's the low frequency difference, which is designed to kind of pull out the radio emission or the high frequency component, the dust emission. The green is a low frequency difference designed to kind of pull out the synchrotron. And blue, which doesn't show up too well, is an intermediate band which is designed to pull out the free. But only approximately, and actually disentangling these components in detail is very tricky and subtle. And we tried a number of kind of old and new, a mix of old and new methods in revisiting this separation problem in the 9-year analysis. Our standard technique for cleaning foregrounds is just to use standard spatial templates that trace these emission components. So essentially the Haslam map for the synchrotron term, the H-alpha compilation for free, and some dust, COBE and IRAS-based dust templates for the thermal and spinning dust. And that's just for cleaning, for doing the CMB analysis. For actually trying to separate these now in more detail, we had 3 techniques I'll talk about very briefly here. One is an old one that we developed in the first-year analysis, a MEM-based fit, where you're basically pixel by pixel fitting spectral components and applying some spatial priors in regions of low foreground signal. And these are the output maps that come out of that decomposition, and you can compare those to the templates, and they bear a lot of resemblance to the templates at high latitude where the signal is weak, and the prior on the template is fairly strong. Sorry. So that's that. There was another kind of an MCMC-based pixel space fitting spectral components, pixel by pixel again, with some other constraints, and incorporating also Haslam and polarization data simultaneously in the fits. And that produced this decomposition. So I'll just blink here between the MEM and the MCMC. And especially if you look at the free map, that's the one that's getting the details of the microwave free is really fairly method dependent in my experience. So you can see going between these two that there's lots of differences in detail in what we think the microwave free component is. And then there was one last pixel-based method, similar in concept but different in detail and execution, that produced a similar decomposition. And again, you can see the free differences. And there's actually regions where the free just goes away entirely in this concept. The spinning dust template is also somewhat, variable and method dependent. So I would say I'm not very happy with how this decomposition turned out, and I'm not really going to say too much more about it. I'll just make a few comments on general aspects of this and move on to the cosmology. So point one is that all of these techniques do a poor job of taking out foregrounds. If you're really trying to separate components and understand them, it's also hard to simultaneously clean sufficiently to produce a clean CMB map in the galactic plane. Not really surprising, and not really an impediment to doing cosmology since you cut that anyway. A more interesting and somewhat puzzling result to me is the map. We also get a map of the synchrotron spectral index, the steepening as a function of, or the steepness as a function of frequency. And we very robustly see a fairly flat index synchrotron in the galactic plane, and we also see a flatter component. So this is now minus 2.6 in temperature units is red. So the green here is going to be about -3, maybe minus 2.9. So we see a flatter component in the galactic bulge, if you will, and then typically falls off steeply on out on the high latitudes. But we don't see. I keep hearing that evidence for the microwave haze requiring synchrotron of flatness comparable to the galactic plane, 2.6 or 2.5, and we just don't really see that in these kind of decompositions, and I'm not really sure how to reconcile that with the haze analyses that other people do. So I'd like to learn more about that. And another feature that's fairly robust, and Planck sees this as well, is that the thermal dust models, the Finkbeiner-Davis-Schlegel prediction for the dust based on extrapolating IRAS and COBE data down to microwaves, systematically, it actually does quite well, but it systematically misrepresents the galactic plane. So this is a ratio along a longitude profile of the FDS prediction to the what we think is the best guess of the microwave thermal dust, and FDS overpredicts it by about 20% in the inner plane and underpredicts by 10 or 20% in the outer plane. And the Planck dust results are seeing very similar things. So that's enough about foregrounds. There's a kind of a fairly simple way to just make a nice picture, which is what the ILC method that we used back in year one, and pretty much stuck with it for a full 9 years, and so everybody's seen this dozens of times, if not more. So I won't really say anything more about that. But this is the downside of the ILC is that we, of course, smooth the data down to our lowest angular resolution channel, which is 0.8 degrees, the K band. Actually, this is smooth to 1 degree. But we can, but of course the W band data has 0.2 degree angular resolution, so we can just do template cleaning on that to produce a higher angular resolution CMB map. And this is the W band WMAP map, taken now smooth or cleaned with the spatial templates I showed at the beginning, but instead of using the FDS dust template, we've used the Planck 353 gigahertz channel because it has a better prediction of the microwave dust emission. And that looks pretty good. And if you compare it to the Planck SMICA map, it looks really good. And I show this to kind of make the point that we're really observing the same sky, and we're observing it in the same sky in great detail. Right? So that's what. So I just saw this for the first time a day or two ago, and I can't stop doing this. So. Of course, we only have 12 arc minute angular resolution. Planck has 5 arc minute. And that doesn't really show up on a projector like this, especially with this kind of spatial resolution. So this doesn't really do justice to the true fidelity of the Planck map. But it is nice to see that we're not just getting the same power spectrum modulo % or 2, but we're getting the same phase in great detail. So, and then this is our kind of final rendition of the bullseye, the acoustic rings in the CMB from the 9-year data, basically taking every hot spot and every cold spot in the map, stacking on those positions, normalized to the peak amplitude. And the stunning thing, of course, is that the BAO jumps right out. And this is, I find, a wonderful way to explain acoustic phenomena to not only to the public, but to general physics talk audiences, to colloquium audiences. There's a much more intuitive picture of what's going on in the CMB than the power spectrum. And people can really understand it, and I highly recommend it. And I know you guys have done a similar version. And to me, this is actually the most beautiful result from Planck. And this really highlights the true power of Planck, right? In having a high enough angular resolution and sensitivity to make this to just unbelievable fidelity. So if you go back to this map, you don't really see that much of a difference on these scales. But if you go to the bullseye, it's dramatically improved, right? So this, to me, really captures the dramatic advance that Planck made. It should have been on the front page of every newspaper along with the map as an indication of what you're actually observing. This is physics written directly on the sky, and people can understand sound waves. Right? But I'm sure that it's going to be a standard picture in every astronomy textbook going forward, as it should be. So, okay. Let's see, back to WMAP briefly. So this is the final 9-year power spectrum, and of course the Planck version goes well beyond the right side of this axis. I just want to make a couple of comments about some of the new approaches we took to estimating the power spectrum in the 9-year data. Kendrick Smith had come up with a nice estimator for essentially optimally estimating the power spectrum across the full angular resolution of WMAP. Coming up with a method for evaluating essentially inverse covariance matrix times the data set, and then projecting that into ALMs and making an estimator which is essentially optimally weighted ALMs squared and turned into C sub Ls. I won't go into the details, but that produces the spectrum shown in the black points, and the red points are our previous method for doing spectrum estimation, the wonderfully simple master method, which I think is quite nice. And these are some tests of this estimator taken on simulations, just showing essentially that we get unbiased recovery from this fully optimally weighted test. So this is just output divided by input in Monte Carlo simulations, smooth to a delta L of 50. And then this is an actual comparison of the 9-year data estimated in 2 ways. It's the fractional difference between the optimal estimator and the master estimator evaluated on the 9-year data. And it's nicely consistent with 0, except there's a little bit of a dip at low L in the kind of, especially in the kind of 30 to 60 L range that we don't see in simulations, and we don't necessarily see as quite as big a dip if we take a larger sky cut. And this is one of the things that troubled me personally for a while. And we convinced ourselves it was not as systematic in the data, and we could not identify any galactic residuals that might be producing this, so we just put it out there as is. But to this day, I don't quite understand why that dips down like that at a few percent. So having this optimal weighting basically lets you squeeze a little bit more sensitivity out of the data relative to the master estimate. It's about 15% in the mid-L range. It works best essentially where the signal and the noise are comparable, so that you're optimally combining signal plus noise. In the low L side, you can just do a pure signal weighting, and the high L side, you can do a pure noise weighting, and you kind of get to an optimal method. But this gets you a little more mid-L range power. And then this is really the cosmological legacy of WMAP, was the standard lambda 6 lambda CDM parameters and the derived parameters that go with it. And I won't bother to read all the numbers off because you're familiar with them and have your own versions. But this is our final look at final pre-Planck look at cosmological parameters from WMAP. I just make a point that WMAP was never designed to be used in isolation, so we always anticipated that higher angular resolution CMB data and complementary data sets would be available, and this was the final compilation from that. And then here's the comparison now with the one version of the Planck parameters, and I wanted to pull out the two completely independent estimates of the CMB sky, the 9-year WMAP alone, and the kind of the CMB plus lens combination from WMAP, which gets its information about the optical depth, which normally comes from polarization data, comes from lensing data in this case, so it's completely independent across the board. And of course, you see this, these are the sensitivity ratios or uncertainty ratios, and in the matter composition, the Planck numbers are typically 25 to 35% more precise. The amplitude, which is expressed in different units, is a factor of 2 more sensitive, and so forth. And the parameter values have shifted by about 1 WMAP sigma, typically, in different directions, and it produces a little bit different fit, a little bit different shape model. I'll just highlight what this last number here, the acoustic scale, which is really the number that Planck improves, the single number that Planck improves on the most and is reflected in the higher sensitivity bullseye. That's more than a factor of 3 times more sensitive in Planck than WMAP. And that's fantastic. So the reason I picked out this combination is because it's completely independent of the WMAP polarization. I've struggled with WMAP polarization for years, and it's the part of our data set that I'm least comfortable with. And here's why. Here's one reason why. And so I was very happy to see this estimate of tau from CMB plus lensing combination of Planck being wonderfully consistent with WMAP numbers. This is the low-L EE spectrum from our 3-year release, and I'm just showing the point I want to drive home here is that the raw spectrum here, and the green and blue points are without foreground cleaning, and then the black points here are the cleaned version. So we're doing heavy cleaning in the EE spectrum to get cosmological tau, and these are low signal-to-noise measurements, so there's all kinds of reasons to be nervous about this measurement, and I truly look forward to Planck getting polarization data and seeing this independently in polarization. And I will say that the primordial spectrum parameters are the numbers that will improve most in Planck when the low L polarization does produce a better measurement of tau, because that breaks degeneracies with the primordial parameters. And so there's significant, I expect significant improvement in these uncertainties and going forward with Planck. Let's see, so let me just briefly comment, and I don't have any final comments on this, but this is a direct comparison of the spectra from Planck and WMAP. Chris Gorski provided these for me last night, and this is basically just taking the maps, applying the same cut and the same spectrum estimation methodology to the data, and then just plotting it from, low L from 0 to 400, so just covering the first peak. Top left is V-band, is WMAP, V-band, and W-band. So these are two different frequencies in WMAP. The same 2 frequencies are close to the same 2 in Planck. And so both data sets are internally consistent across frequencies, and in the case of Planck, across instruments and across angular resolution. This is a comparison of the low frequency V-band to Planck 70 gigahertz and the W-band to the Planck 100 gigahertz. And what you see here is that there's typically the WMAP points are about 2.5% higher than in Planck in this L range. And if you plot this as a ratio, at the bottom 2 panels here, you get the 70 essentially the 70 gigahertz and 100 gigahertz comparisons, they're quite consistent with each other, and they're about 2%. Planck is about 2.5% lower than WMAP across the first peak. And I don't know why. I will just speculate on a few things on the WMAP side that I'm familiar with. And one question is, could this be an effect of a deconvolution error on the WMAP that we're not measuring our beams correctly, and therefore not deconvolving the power spectrum properly? So there's a question as to whether or not our beam uncertainties, so what I'm plotting here for our different detector channels, have this shape where they essentially, since we normalize to L equals 0 or L equals 1, there's no uncertainty at low L, and then it rises up to a plateau at about L of 100 and levels off. And the shape of this is dominated by our uncertainty in our solid angle measurement, the total area of under the beam. And that's typically about 0.5% per detector, and as shown, has this shape. So basically, you kind of have a freedom to shift the ratio of the low L to high L data by about 0.5% per channel. I'm running out of time, so I'm not going to go into all the details of the physical modeling that we've done with our beams, but I will just say that our primary tool for measuring our beam response, and these are focal plane maps now taken from in-flight observations of Jupiter, and then we do a physical optics model and show that comparison in the middle and the residuals on the bottom. We basically combine the Jupiter measurements where the signal to noise is high and regularize that with a physical optics model out at the edges where the signal to noise is low to measure the beam response and transform that. This is the distortion that we fit to on the mirror as a result of fitting the Jupiter observations to essentially Fourier distortions on the mirror. And one kind of cool but ugly thing you can see in this is that there's a depression in the middle, and you can see clearly the A-frame support structure of the mirror. Looks just kind of like a washcloth hanging over a rack a little bit. And this is the primary, secondary on the A side and the B side. And you can reconstruct beams using various, so we basically expand the distortions in Fourier modes as a function of spatial frequency, and you can reconstruct the beam response up for a variety of different Fourier cutoffs. And you can kind of construct the tail of the distribution here. The take-home point I want to make, though, is that at the end of the day, when we go back to these beam maps, essentially 99.8% of our solid angle is coming from regions in this data that is directly measured by Jupiter. It's not based on the model. So we're only getting about 0.2% of our solid angle measurements from this physical optics model. And I am now out of time, so I'll cut to the chase and just make the final point that because the WMAP spectrum is higher, if we're misestimating our beams, the sign of it has to be that we're overestimating our solid angle and therefore over-deconvolving our raw measurements to produce a higher spectrum. So the most that we can be overestimating the solid angle based on modeling errors is 0.2%, because that's all we get out of this. And so but we need something like 1.2% to explain the difference with the spectra here. So if that's the case, then it has to come through some error in the processing of the Jupiter data that we haven't uncovered yet. And I will never say that's impossible, but it's very straightforward. It's basically just taking data, binning it, transforming it into harmonics, and applying it to the spectra. So I don't have an explanation for this yet, and I'm not going to say anything more beyond that, but it's something that we're going to be looking at carefully, because despite the fact that we have these wonderfully consistent maps, we all care about the details, and this is really supposed to be precision cosmology, so we want to really understand this, even if it doesn't dramatically affect cosmology. So let me just stop at this slide, and I'm going to wave my new flag for a second, and I won't say anything. I won't go beyond this, but just point out that I moved to Canada 2 years ago, and I'm excited to talk about a new project that we're getting started up there to do a large-scale structure measurements. And this is an experiment that we call the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. It's going to be a 100-meter by 100-meter radio telescope situated in Penticton, British Columbia, at the Dominion Astrophysical Radio Observatory. And the goal of CHIME is to map essentially half the sky in neutral hydrogen to measure the BAO signal, to try and hopefully probe dark energy a little bit. And this is something that we just received funding for from the Canada Foundation for Innovation last couple months ago. So we started groundbreaking on this last 2 months ago. In fact, just close with one more photo. And I don't want you to think that this is a mass grave in preparation here, but it's just groundbreaking, and we're putting in the footings for a new radio telescope that will do another large-scale structure measurement going forward. So thank you very much.
Okay, thanks very much, Gary. Do we have some questions? Reino, if you just wait for the...
Should be working? Okay, I think it's working. Gary, thank you very much for the excellent talk, and congratulations.
No.
Okay, let me see if it works. Hello? Okay, it works. Congratulations to the entire WMAP team for the excellence reached in the results.
And congratulations to the entire Planck.
You have reached, I think you have tracked the right road, even to Planck. Now, the question I have is, both instruments, both missions see some anomalies, say the hot spot, the cold spot, sorry, and some kind of isotropy, statistical isotropy into the map. Do you have any idea of the significance of those anomalies, and should we catch them up or not?
I'm officially agnostic about the anomalies. So, it's so much on the border, and I really don't understand well enough how to quantify the posterior biases that are involved in these measurements. So I really don't know what to make of them, and I really think we need the guidance of theory to be able to interpret this. What I would love is for there to be some potential posterior explanation of these effects in the CMB that can then make a prediction for what you might see in large-scale structure as a further test of this. And if that actually comes to bear, then we actually have a chance of applying the scientific method to these questions rather than statistics. So.
Okay, Paolo?
Yeah, this is more technical about the two power spectrum estimators that you have worked on. And you said that when comparing the optimal estimator and the master estimator, you see a discrepancy that is not justified by simulation. If I well understood, that happens in a region where the CMB itself is kind of anomalous with respect to lambda CDM. So how statistically significant is that, and can you say something more?
So when we did our simulations, we found something like a little under 0.5% of our random realizations had an effect like this in the realization. So it's kind of unusual at the 0.5% level, like every anomaly we encounter. Right? And again, we don't see this switch if we go to a slightly larger sky cut. And we were suspicious that somehow this optimal weighting was kind of picking out galactic emission, on one side or the other. But we saw there's really no evidence that that's actually the case. And so it's another one it's my last 0.5% effect in WMAP that I'm aware of. And so I'm going to stop looking now. So.
Okay, time for maybe one more question. Okay.
I have a question about the side lobes. You showed how you estimate your side lobes via physical optics. Do I remember correctly, or am I wrong, that you also had some measurements of the side lobes? Is that true? And how did they compare with the physical optics simulations?
So let's see. There's one plot I should have put in this talk and I didn't, but there's another one that is in here, which is, I think it's in here afterwards. Yeah. So we had we were able to observe the moon on the way out as we did 3 phasing loops and we had a fairly close approach to the moon in the first week of the mission. So we were actually able to observe about 2 pi, half the sky in the moon data. And we saw these really actually wonderful and awful at the same time maps of the spill around around the edge of the primary, which actually showed diffraction in the data. I don't have that picture here, but this is a compilation of moon observations out to about 40 degrees, so going way out into the tail of the beam, and comparing to the extrapolation of the best fit physical optics model in green. So not every channel is perfect, but they actually do come out quite good in this case. And the amount of solid angle contained out here is actually tiny, and I think we do have a pretty good handle on that. And I'm pretty confident that we're not dramatically overestimating solid angle because there's just not that much. Again, we only have 0.2% in our model here.
Okay, well, let's thank Gary again.